So for this example, a researcher claims that 51% of adults believed incorrectly that antibiotics are effective against viruses. That's right, bookending this chapter. In a random sample of 2,202 adults, 1,161 say that antibiotics are effective. At alpha equals 10%, is there enough evidence to support the researcher's claim? So again, because that alpha is a little bigger, and in this case, based on what the researcher's claiming, we might be looking a little bit more for some strength here. We're a little bit more willing to kick out something that's actually good. But anyway, for our first step, we want to check that things actually work, where I'm not going to write it out this time, but it's the same sort of idea as before. NP, NQ, it's 2202 times basically anything is bigger than 5. So that's good on both counts. In this case, they're pretty close to 50% in particular, as P is 0.51 and Q would be 0.49 as a result. Like I said, it's usually free, but still good to be sure. Going on to more thoughtful things, we want to talk about our hypotheses and claim. We are working around the researcher's claim that 51% of people have this misconception. The opposite of that is that it's something else. So the null is our claim, and the alternative is its alternative. So actually, I should have been a bit more careful with my wording when I was first talking about that value for the level of significance. Like I said, the level of significance here is 10%, and to be sure, this will be a two-tailed test. But because they're taking a level of significance 10% and they're claiming the null hypothesis, they're actually kind of calling their shot here. They're saying, I'm really sure that this is good because I'm going to leave myself even more error than I normally would need to. It's a really confident researcher today. Let's see if they're actually, well, good. But anyway, this is our setup. So from here, if we want to talk about how we would test this hypothesis, well, what we have to be cognizant of is what approach we want to use. Again, if we want to use a p-value approach, we would then go on to get our test statistic. We're going to need that anyway, but as I said, I want to do at least one critical value problem in detail so you can see that as well. So if you want to do this using a critical value, you'd need to get the breakoffs. So those critical values, which I'm going to denote Z0, even though it's technically two of them, would be positive and negative, because this is two-tailed, inverse normal of what's going to end up being 0.9501, where it ends up being 0.95, because you've got 10% that you're splitting between the two tails, so you want 5 in one, 5 in the other. You've got 95 to the left of the big one, or 5 to the left of the small one, depending on how you want to see it, depending on what functions you have to work with. Or just the table. Some people prefer the table, but nah. Anyway, what we'd end up with there is an incredibly common pair of critical values at plus or minus 1.645. So if you want to talk about our rejection regions, those would be above the big one and below the negative one. That would be Z greater than or equal to 1.645, less than or equal to negative 1.645. That serves the purpose. I'm being a little shorthanded because, again, I'm not the biggest fan of the critical value method. Anyway, these are our rejection regions. From there, we do need our test statistic for the purposes of comparison, and I'm going to use some really shitty notation here, but bear with me. In this case, we have a value for X, the number of people from their study, 1,161 over the total number of people in the study, 2202, where that is our p hat. P in this case is 0.51, and we're dividing by the very ugly p hat, or not p hat, p times q over n. Again, these numbers get uglier the further we go, and in particular, I mixed dealing with fractions and decimals. You don't like to do that generally, but being lazy. Important thing is, you should get an approximate z-score here of 1.60, where you want to be sure here that that 1.60 also gets doubled onto the negative side, because, remember, we're dealing with a two-tailed test, so you kind of get the other one for free. And importantly, for our purposes, this is really close, but that 1.60 is smaller than 1.645 and bigger than negative 1.645. So, because our test statistic is between the critical values, which I'm just going to abbreviate CVs, we would again fail to reject our null hypothesis. We fail to reject the null because this value lands in the middle. Technically, the other one does too, but a little bit less interestingly, even though if we look at this distribution, as you can see popping up here, it is very close. This researcher was probably sweating a little bit, but their confidence did pay off here, as if we want to talk about what would happen for their conclusion, what would be the interpretation, we could say something like there is not enough evidence for alpha equals 10% to reject the claim that 51% of adults incorrectly believe that antibiotics are effective against viruses. Still works in exactly the same way. It's just a little bit tighter, but importantly, we are not in the rejection region here, so we would fail to reject, and thereby fail to reject the claim. And again, if we wanted to deal with this using the calculator, we could. That one proportion z-test, even though it's not great for critical values, it still would get us the p-value we want here of 0.11, 11%, which would be bigger than our value alpha. So for roughly the same reason, we would still fail to reject the null hypothesis using the p-value method if we prefer, and the calculator with whatever other methods you want to use. But that's how we'd approach basically any of these problems. So that's it for Chapter 7. That's it for Unit 3 as a whole. With that in mind, good luck finishing your preparations. Good luck on the exam. And I'll see you next time, where we're going to move in to our last unit of the semester, Chapter 8, where we're going to talk about these same flavor of things, but instead of looking at a single parameter and seeing if it holds up, we're going to compare values from different parameters that may have a relationship, may have a connection, may be right for some sort of comparison. I think you've got bigger fish to fry at the moment. I'll see you then.